With that, Long is going to be giving our first talk of the day. Alethiometer?
Yes.
Alethiometer.
Good morning, folks. Ilian, can you hear me? Or folks on the Zoom or what? I guess. Oh, sorry. I thought you were on Zoom. Anyway, so I'll be talking about my debugger for program verification called Alethiometer. We live in a very exciting time for formal verification because in the last several years, researchers have formally proved the correctness of increasingly larger, more complex, and more realistic real-world programs. However, formal verification still is not widely adopted in the software industry, in part due to the fact that formal verification is very difficult. It takes an order of magnitude more effort to prove the correctness of a program than to write the program itself. For example, one of the seminal landmark papers in formal verification describes a operating system microkernel called SEL4. However, even though the implementation itself was only 10,000 lines of code, C and assembly code, which took 2.2 person-years to write, the spec was 200,000 lines of Haskell invisible error improver code, and took 20 person-years to write. Another landmark project is the CompCert verified C compiler, which has a spec using the ROP proof assistant that is roughly an order of magnitude greater than the code itself, which was written in OCaml. It's thus evident that in order to make formal verification practical, we must reduce the burden and difficulty, and therefore cost of writing formal specifications. There are roughly two major approaches to formal verification of software. The first approach involves using interactive theorem improvers or proof assistants such as Lean or ROP, which we will not explore here. Instead, our research focuses on deductive program verifiers, also known as autoactive verifiers, which are built upon more familiar-looking imperative programming languages. The most well-known autoactive verifier is Daphne, which uses its own object-oriented programming language reminiscent of C# or Java. Another popular autoactive verifier is Varus, built on top of Rust. The programmer annotates each function or method with preconditions, postconditions, and loop invariants, and the verifier uses an SMT solver to automate discharging verification conditions, making verification less tedious compared to using a proof assistant. During my first semester, I began my research by learning to use the gradual CNOT verification tool. This is a tool that was developed by Jonathan Aldrich's previous student, Jenna Wise-DiVincenzo, now at Purdue, for her gradual verification research project, which was aimed to bridge the gap between dynamic and static verification, but that's not really the focus of this talk. So gradual CNOT is built on top of CNOT, a memory-safe subset of C used to teach undergraduates at CMU in the course 15-122, which introduces imperative programming and data structures and algorithms. But in addition to what C has, it has contracts, which are Boolean expressions that are evaluate if the program state is correct. And these in CNOT, contracts are verified at runtime. But in gradual CNOT, it's verified statically. So, as I said, every function is annotated with a precondition and postcondition. Just a quick refresher for folks who are not familiar with deductive verification. They are assertions, so logical expressions together. They state that if the precondition is always true when the function is called, the postcondition must always be true when the function returns. Now, here is a simple example of a function that imperatively multiplies two integers by repeatedly adding the first number. For simplicity, this function only works if the second argument is non-negative, which is specified in the precondition. The postcondition specifies what it means to be, what it means for this function to be correct, which is that the result must indeed return the product of two arguments. Every loop must be annotated with a loop invariant, which is an assertion that must be true when entering the loop and after each iteration of the loop. In this case, the product that is being computed must always equals x times the loop counter. The function in the previous slide only took integers as parameters, but what if we wanted to pass in a pointer which points to a data structure on the heap? To reason about data structures on a heap, in 2002, John C. Reynolds at CMU introduced an extension of Hoare logic called separation logic. And gradual C0 uses a variant of separation logic called implicit dynamic frames. And I'll quickly explain how they work. So if a function wishes to read or write to a field of a struct, the precondition must specify a permission to that field of a struct. When a function is called, the caller passes in the permission to access this field. And when it returns, the permission is returned to the caller. So this is just a function that negates the value of the first element of a list that's passed in. This is just a simple linked list. The function in the previous slide can only access the first element of the list. What if we wanted to access the rest of the list? Implicit dynamic frames also feature predicates, which abstract over assertions and allow reasoning about heap data structures of unbounded size. Predicates have a body, which is a logical and expression consisting of one or more permissions, assertions, or other predicates. The meaning of a predicate is that this predicate is true if all the permissions in its body are held and the assertions are true. And the predicate can refer to other predicates in its body. So those predicates must be true as well. And recursively specifying predicates is how you specify data structures like lists or trees. So let's write a function that recursively negates the entire list. Now, if we verify this function, it would fail because predicates are what are called isorecursive. They are isomorphic to, but not equivalent to their bodies. The assignment to L arrow value would fail because the permission in the body of posit list predicate is not accessible. To gain access to this permission, you must perform an unfold operation which exchanges the posit list predicate with its body, exposing the predicate permissions within. The reason why predicates are recursive is because predicates can be recursive, and without explicit unfold operations, the verifier does not know when to stop unfolding. We're potentially building an infinitely long SMT query. And a fold is the inverse operation to an unfold. So it looks to see if the permissions inside the body of, say, of this neg list are currently held, and all the assertions inside neg list are true. And if that's so, then it exchanges the permissions with neg list. And you have to, in this case, you have to fold neg list in order to ensure the post condition. So our experience was that using the gradual C0 command line verifier was very challenging for several reasons. Writing implicit dynamic frames annotations was very challenging because it was tedious to keep track of whether predicates were folded and unfolded. Furthermore, all active verifiers, Daphne, Varus, and gradual C0 have challenges due to their use of SMT solvers. Active verifiers allow more automation than proof assistance, but when a verification failure occurs, it's difficult to understand why it failed and where the verification failure occurred or how to fix it. The main feedback the developer receives is the verification results, success or failure, without no visibility into the verifier or solver's internal state. To deal with some of these challenges, we turned to the work of Brett Victor, a visionary UI UX designer who worked at Apple and who collaborated with Alan Kay to build a research lab called Dynamic Labs. In his seminal Inventing on Principle talk, Brett Victor declared his guiding principle, which is that creators need an immediate connection to what they're building. He explains the meaning of this principle is that when you're making something, if you make a change or that you make a decision, you need to see the effect of that decision immediately. There can't be a delay, there can't be anything hidden. Creators have to be able to see what they're doing. And he goes on to argue that most coding environments violate this principle and demonstrates tools that enable programmers to see immediately what their program is doing. There are a few more. I think the best thing to explain it is to introduce my debugger called the Alethiometer from ancient Greek aletheia, truth, and metron, measure. And I will demo it right now. It's a plugin for the JetBrains IntelliJ IDE. Oh no, it doesn't show on my screen. So once you type in your program, this is the multiply example that I showed. Type in your program. You can call it. You can call this verify file inline. There's also a key shortcut as well. So as you can see here, there's annotations on the right side of the code, and on the left side of the code is what is called Debugger, and it shows all the symbolic execution paths. So right now it's showing the path into the while loop. So you can see all the facts we know here. So the beginning, we know the precondition. And then when these variables are assigned, we have them. So this is what the facts we know and entering their loop. Most notably, for variables that are assigned inside, we lose those facts. So that's shown as well. So before those product x equals 0, and now we see the loop invariant. And so now I can switch between different paths. So now this is the path where you exit the loop. Let's take a look at the negate list example I showed previously. Let's try to verify it. So now we have an error, which is that assignment might fail. There might be sufficient permission to access this, and that's because I don't have the unfold expression. So let me add that. I have a different error, which is that post condition might not hold because there's no neg list in the heap. And I forgot to mention that it also shows the purple boxes show the currently accessible permissions. So so we have the permissions to so after the unfold expression, pos list disappears. Now we have the permissions to L value, L next, and then the predicate pos list L arrow next. So because this post condition is hold because we don't have a neg list, so we need to fold neg list. We have a different error that assertion L arrow value minus 0 might not hold, and that's because we have a little bug here. It could be 0 in the precondition. Now that we fix it, there's verification successful, and you can see both paths. The state of the heap. So like all the permissions and the predicates at each line of code, as well as the path condition or the expressions that are true at each line of code. Under the hood, it's built on top of the Viper verifier infrastructure, which is like a compiler. There's different front ends, and so Grantle is just a front end for the compiler. Just for the verifier. So this you could extend my debugger for any verifier that uses Viper. But just to conclude that the preliminary user studies show that implicit dynamic frames is hard to learn and use even for experienced programmers. Fortunately, substructural type systems can be translated to IDF, and this is what the Prusty reverse verifier does. And so my next step is actually to implement a liquid so at Jonathan's research group, we are working on liquid Java, refinement types in liquid type systems for Java. So for those who don't know, that's types refined with a logical predicate that constrain valid values, which are then passed which are then verified with an SMT solver, and then we combine those with a Rust style like uniqueness borrowing type system for Java. And so the next step is to build this debugger for Liquid Java and LaTeX combo by translating Java to Viper IR. I think that my ultimate long-term goal is to make it easier and less costly for programmers to formally verify the correctness of their programs, which will drive industry adoption of formal verification, and hopefully which will result in more reliable and secure software. Taka?
Yeah, could you talk a little bit more about the user study?
I just tested it with other S3D grad students, and people who had programming experience, and what we found was just even, I guess with user study, you only get at most maybe 1.5 to 2 hours, and if you have to teach people a new concept, I think it's really hard to do a user study. I have a tutorial for teaching people how to use IDF. Even very experienced programmers started using it, they had a hard time. And so I realized that I don't think it's going to work with say undergrads who are taking 15122 because I think it'd be even more difficult for them. Josh?
Yeah, it's really exciting to see that you're making a system here that sort of shows everything. It's very omniscient view. But naturally, a challenge that comes from that is that there's a lot of information to dump out onto the screen. And it looks like, for example, a lot of the things that you're showing are sort of the same thing, repeated from line to line because it persists. And this sort of raises questions about the visual design or the information design or the visualization design. Is that something that you're interested in?
Oh yes, I actually worked a lot. I actually iterated a lot on this just by myself. There's actually different views of this that I didn't get into, showing a diff between line to line. Only the changes between the if something was folded or unfolded, then you would remove. Then you would show what was added, what was removed, and same thing with the path conditions. The problem, this is the problem with doing the user study, is that stuff that makes people more productive with real world examples also have a higher learning curve. So even introducing the diff view for people was actually more challenging. But at the same time, it's more useful for people who using debugging real world bigger examples. And so that's why so this is one of the reasons why I was also wanted to switch to Liquid Java / LaTeX, because the information that my guess hypothesis is that the information you need to show is probably less, even for real examples, than it is for separation logic IDF. Chris?
Yeah, I think this is, since you mentioned the kind of different challenges involved in scaling from smaller, more pedagogical examples to real world uses, something that came to mind for me is, just different contexts, pedagogical context versus, professional setting where you're verifying high stakes kind of high assurance software. So do you think there might be different needs in terms of what is visualized, like the granularity or types of information that's surfaced in those different settings?
Oh, absolutely. I think for pedagogy, and you're going to be doing just simple examples like negating listers, or just sorting or something, sorting. You would show. I think you would want to show everything. You would, whereas for professional stuff, there's getting to a lot more advanced things like fractional permissions. And so fractional permissions, magic wands, other things, quantified permissions, and I actually haven't gotten to super deeply into how to design the view for that, but I think there's definitely challenges with that. Other folks, Sarah.
Have you considered doing a longitudinal study if the learnability sort of steep learning curve is a challenge for study design?
I actually don't know what a longitudinal study is.
I'll write down some notes on my phone. All right, let's go ahead and, sorry.
Sam?
Just a small question. It's kind of similar in spirit to the sorts of UIs you get when working with like interactive assistants like Rock or Agda or Lean. Obviously, they're very different, as you said in your talk. Like those are less focused on like using SMT solvers and more like direct step-by-step or using tactics. But like, did you take any inspiration from those UIs or like make any conscious decisions to differentiate the UI from those tools?
No, because I don't actually know much about interactive peer improvers, unfortunately.
Okay.